Namaskar and welcome to episode number 16 of Understanding Consciousness podcast. Today we are going to go through with the introduction of the paper that we started yesterday. And okay, here's the thing. Frankly, this is too hard. Not too hard. I'm still understanding a lot of things, understanding the mechanism of experimentation, trying to figure out all the previous work done, trying to figure out all the literature that is being referenced in this paper. But of course, this is a huge field of research has been going on for 30 years. I cannot expect to be well versed with everything, and so today I'll just at the start I'll let you know, if you are trying to understand this with me, you should be reading the paper as well, and just comment and let me know if I'm going wrong or something, right? So the first problem that I faced in this paper is that there is a contradiction in the paper. According to me, there was this contradiction that I felt was there in the paper. So yesterday we established that this paper is trying to figure out the mechanism of how the visual sensitivity is attenuated because of your own movements. Your own hand movements they go unnoticed, right? And we are trying to find the mechanism of how the underlying mechanism of this attenuation, right? This is the goal of the paper. The goal, I wouldn't say it's the goal of the paper. This is the field, because it's not going to fulfill that goal in just one paper. It's working towards that goal, okay? And it proposes that active inference, this is what we discussed yesterday, active inference or prediction error minimization theory. First of all, I tried to read this on Google, on Wikipedia, and there are some new terms. Free energy, something called free energy is a part of it. It's this field goes on and on back to a lot of different ideas. I think it's also related to homeostasis in biological systems somehow, which I read from Antonio Damasio's work, his book Strange Order of Things. That's also about feelings and emotions being a part of the homeostasis, the extension of homeostasis. And I think that it is a little related to this. I may be wrong. Anyway, active inference is a big theory. I don't really understand much about it, but I understood this one part of it, that it's trying to minimize the prediction error. The brain is the functioning of the brain is an attempt to minimize prediction errors. I'm interchanging these terms here, but I don't think it should be. So it's the theory, the prediction error minimization theory. I'm reading the paper now. Posits that the brain is constantly predicting sensory input, right? It's constantly predicting what's going to happen. Okay, this is already, we already know that. Okay, predictions are then continuously compared with the sensory input in such a way as the brain makes a prediction, and then they are compared with the actual data, and then the overall goal, and then the error, whatever the error is, it's propagated for further computation, right? And the overall goal of this computation is to minimize this prediction error in the long term. So as your infant brain starts understanding the world, as the newly developed brain comes out and starts getting all the sensory information, from that moment in one's life, the brain is trying to predict and correct itself through this mechanism, right? And that's why infants. This is not in the paper. This is my own attempt at trying to connect all the dots that I know about. So, when initially a baby is born, the visual acuity is not that established. Slowly, the brain automatically tries to establish this visual acuity, and then that process happens because of this prediction. And I think a lot of neural networks are trained with this mechanism itself. Initial first generation neural networks are really bad at doing the task, and then the ones that are not the worst, the ones that are the best, they are taken. The ones that have the minimum error are taken, and then they are made to reproduce into multiple ones. And then these are genetic algorithms, neural networks algorithms, and they have already proven to be successful in a lot of fields, right? So there is some truth to it, in at least in artificial intelligence. um, so but here is this contradiction that comes. Okay, so let me go to contradiction. So the active inference theory suggests that movements are elicited by predicting the sensory consequences of the movement. So it's saying that if you see a glass in front of you and you want to grab the glass, the brain will first predict what will happen when you do that. Okay, this all happens subconsciously. It doesn't, you don't feel it consciously, right? And then the movement, so so these predictions are actually driving. So the brain will predict what will happen, but it's actually not happening right now, because it's a future. It's your hand is resting right now, it's going to move to the glass, and as it moves to the glass, before it starts to move, there will be a prediction of the sensory input. But there is at that moment a difference in the prediction and the actual sensory data. So this paper is saying that this theory is saying that these predictions are actually driving the behavior, so that the organism will perform the necessary movements leading to the predicted state. So prediction is driving behavior so that the predicted state is achieved. However, the predicted consequences, that the hand will move towards the glass, are not in agreement with the current sensory data, where the hand is still resting in the resting position. And so this is where I thought it's saying the active inference theory proposes that this mismatch between the predictions and sensory data is resolved through withdrawal of attention, which I don't understand. I won't belabor on this point. If you don't understand, that's okay. Let's continue on. So I decided to continue on because I've been reading this paper and the things accompanying this paper on Wikipedia since the morning now. It's in 3-4 hours, and all of this is so new to me. Everything is so new to me that it's taking a lot of time. But let's go on. Let's cover all the points that I actually understood. So first of all, this is how are they experimenting this? The experimental setup is very fascinating. There's something called Gabor patches, or I don't know how to pronounce it, but the Gabor, Gabor, I think that's how you should pronounce it. Gabor patches are these line gratings. I'll show it on the video. If you're just a viewer, just search on the YouTube. If you're just a listener and you're not watching a video, go to Google and search for Gabor patches. But here it is on the screen right here. This is Gabor. This is the Gabor patch. And the Gabor patch is, for those who are just listening, it's a it's a zebra crossing kind of a pattern, black white lines, and it's also there is an it's enveloped by the Bayesian distribution. I think that's what it's called. Maybe I'm wrong, but it's like a splotch. It's like a circular splotch of black and white lines. The center of that circle is the most contrasting, like the most the strongest contrast between the black and white lines. And as you go towards the edge, it fades into grayness. Okay, so I don't know why these are the most crucial, but I think they trigger. If I have to guess, they trigger some visual neurons, the edge detection, and all those things, and the difference in contrast. So they are very visually exciting. Not exciting as in exciting to us in conscious state, but exciting to the neurons, excitatory to the neurons. Okay, they trigger a lot of visual sensitive sensations, so they're considered good for testing. And so this is the experimental setup. First of all, they are testing two things. First is sensation, actual sensation of. So okay, before I go into that, this is what it is. A person is sitting on a chair. There is a screen in front. There is a dot in the center of the screen where the person has to look all the time. Okay, on the left of that dot, on the left side of the screen, there is one Gabor patch. On the right side of the screen, there is another Gabor patch. All right, and the test is to decide which, just look by looking at the center, while looking at the exact center of the screen, that dot at the center of the screen, it has to, the person has to decide which of the two patches are more or stronger contrast, which of them, which are more faded and which are less faded, so just visually which is more contrasting. And the orientation is different in both of them, as in the lines are not exactly vertical or horizontal. There is an angle to the lines. And what is happening is, with the hand thing, they move their left hand. Half of the time they move their left hand to cover the left Gabor patch, but the VR, the virtual reality goggles that they're wearing, oh yeah, they're wearing a virtual reality goggle. They are not even, it's not a screen. They're not looking at a screen. They're looking into a virtual reality goggles. And as they move the hand towards the left Gabor patch, to cover the left patch, as soon, and the there is a hand tracker attached, and it knows when the hand has covered the patch. And the virtual reality goggles do not show your hand. They only show the screen, but the mind knows that the hand has moved towards that. Okay, through proprioception, right? And this is what is being tested. How good is the hand? So without the hand thing, you would be able to tell. I mean, I don't know what the simplest experiment would be, just showing which of the two sides contrasts. I think everyone would be more or less almost 100% in telling which is the more contrasting patch, the left one or the right one, right? But when the complication occurs, when there is a perceived hand in front of the patch, the mind should attenuate the sensory input coming from that position. So if the hand is in front of the left patch, what should happen is that if is that the left patch should feel less contrastful than the right patch. Okay, and they switch the hands in this middle of the experiment. And there are other experimental setups which we'll discuss tomorrow. The way the input is being entered, the way the control. So we'll discuss that tomorrow. But today I want to discuss this one thing called metacognition, which I understood what it is. Metacognition is cognition about your own cognition, knowing about your own mind and its working. It's metacognition, basically. Meta of something is just a cycle on its own, on itself. So in this case, in our case, metacognition is, first you ask the person which of the two sides are more contrasting. And the second question which comes under metacognition is, how confident are you about your choice? All right. And both are being tested. The metacognition also appears to be affected by this kind of visual occlusion. Am I using the right word? This attenuation, the sensory attenuation. They are trying to test whether you feel like you're less confident or more confident. And then there is a control guy, which does not have the control condition, not a control guy, but the control condition of the experiment 2 would be when the hand comes in front of the patch. The patch is never shown behind the hand. It's just away from the hand. It's a control. It's the opposite of what the control. This is what, if you don't know what control is, a control of an experiment is just a negative of the experiment, such that the rest of the things can be statistically taken out. The rest of the side effects of the way you are doing the experiment, all the unknown side effects can be separated from the actual effect that you are trying to study. The actual effect is, in this case, is whether the hand in front of the patch does something to the sensory input. How do you control it? The hand is not in front of the patch. And what happens then? What happens to metacognition, to the confidence in your own ability in the second sense? So, I've gone 18 minutes. I didn't know I had 18 minutes worth of material today, because I frankly am not confident about this paper yet. There is so much to learn. There's so much research. Brown et al. 2013, Clark 2015, Locke et al. 2017, Limanowski et al. 2018, then Carrasco et al. 2004, and so much research which has already gone in it. But I'll try to get past it and try to understand this particular experiment and how this goes, and we'll see what we can take out from it. But what I understand from it is, it's the experimentation itself is so fascinating that I actually want to do it. If it's available online somewhere, I would love to do it, just be a subject. And maybe as a programmer, I am actually fascinated in creating this, how to create this and get people to do it. And this is fascinating. This is just, I almost want to go and ask them, can I be just a lab technician and just be around you guys when you do such experiments, just be around you and just be amazed by all this. This is a newfound fascination I have, because first of all, One thing is it's hard, but it's not very very hard. It's not. There is some mathematics, but it's not a lot of mathematics that it scares me. And I'm looking forward to understanding this paper. The more I read, the more I get, the more gets through into my mind, and the more I will be able to explain on this podcast. So thanks for listening, and see you tomorrow.